Hi everyone, this is a small introduction to our work optimal hacking sensing with process and measurement noise. The goal of our work is to increase the estimation performance of an extended Kalman filter by developing an intelligent control strategy able to maximize the amount of information gathered by the robot sensor and, at the same time, limit the negative effect of the actuation noise, which basically degrades the above-mentioned information and is far from being negligible for several robotic applications. We used as information metric the smallest eigenvalue of the inverse of the covariance matrix, solution of the Continuous Riccati Equation, and we determined the inputs that maximize this value. This corresponds to minimize the maximum estimation uncertainty. We formulate our problem as an optimization one. In order to reduce the complexity of a problem and to better cope with the real-time constraint of an online implementation, we make two simplifying working assumptions. First, we only consider differentially flat system. This allows avoiding the numerical integration of the nonlinear dynamics of the system, reducing the computational cost. Second, the trajectory is parameterized as a B-spline. This assumption allows to reduce the complexity of the problem from an infinite-dimensional optimization into a finite-dimensional one, where the optimization variables are the control points that determine the shape of the B-spline. Our objective is the maximization of the minimum eigenvalue of p at -1. This maximization minimizes the maximum estimation uncertainty of the extended Kalman filter, actively improving the estimation process. For ensuring the well-posedness of the optimization problem, we take into account three constraints: the control effort, the flatness and regularity, and the state coherency. We then design the control by resorting to a task priority approach. Here we show our proposed solution for the unicycle case. We start from the prioritized task control that takes into account the task described in the previous slide. The output of our controller is the velocity of the control points, that moving modify the overall shape of the trajectory followed by the robot. Then a time law is applied on the B-spline and, thanks to the flatness, the algorithm computes the input for the robot, defining also the current control effort. The robot executes the given inputs and acquires new data from the environment through its sensors. These measurements feed the extended Kalman filter that provides an estimation of the state of the robot. The estimated state, together with the covariance matrix provided by the filter, are sent in real time to our controller, beginning a novel iteration. Thank you for your attention. I hope to see you at the interactive session.